All right, so hi, welcome to The Platform is Dead, Long Lived the Platform. If you're asking who is this guy, that was a nice introduction, but my name is Luka Kladaric. I'm a chaos manager at a consultancy called Sakura Collective. We deal with chaos. We don't do greenfield development. We don't do features, buttons on websites. We won't build your mobile app. If you're drowning in tech debt, if you have performance or security issues, we'll put you on the right track and then hand off to someone who deals with normal development. I'm also an architecture, infrastructure, and security consultant. I'm a recovering web developer of over 10 years. Also a New York-based startup founder and a remote work evangelist. I've been working remotely for over 10 years from Croatia. So before we get into the talk, I'll be what is the platform that I'm talking about here? I'll be talking about internal hosting platforms, so the shared environment that all engineering teams use to host any kind of backend application, web or otherwise. So 2 years ago, I talked at this very conference about zero downtime data center failovers with the subtitle of Switching Hosting Providers for Dummies. It was a talk about how we escaped a sinking cloud provider and ran away to AWS and the tech stack that let us execute that migration. So I'm here to update you on that deployment and the pain that we noticed over time and what we replaced it with. So let's quickly look at what the stack was comprised of. It was Ansible. This was our config as code, tech of choice. You declaratively describe how you want your servers to look like, how you want them configured, which software you need installed. But we also abused it for deploys. We use Jenkins as our CI/CD tool of choice, building artifacts and shipping them out to servers and shipping the artifacts and configurations using Ansible. We learned from mistakes of past where people use the Jenkins UI to create jobs. So the last instance that we used had a dedicated repository for housing all of the jobs. It was config as code, of course. So you can do inheritance in your build jobs. All Android apps build the same way. All Python apps build the same way, and you only define like the differences between them. It's great. I loved it. I still love it. We still have a tiny bit of it. If you're familiar, so I contributed to building it, so I'm very familiar with it. I know exactly where each thing is found, but it's impossibly complex to jump into. Like if you're just a web developer trying to change how you're like trying to add one thing to the way that your application is built, it is absolutely impossible to pick up. So we also had HA proxy. It's a load balancer software. We had it auto configured from Ansible, so I don't really know what the HA proxy configuration file looks like. We just, when we define a web application in Ansible, it would automatically be added to our HA proxy. HA proxy is very powerful, very flexible, very performant. I was a big fan. And we used Nginx. Nginx is a web server. We needed this on the machines where we had our applications because we would host multiple applications on a single machine. So we needed something that could route requests to the appropriate application based on vhost. I'm talking about web applications specifically here, but there's other stuff. But it was one more thing to keep track of. It was mostly in the way. I don't remember any situations where it helped us. I can remember many situations where we had some sort of incident because of it. We also used Isinga. It was our primary monitoring solution. It was, again, auto-configured from Ansible, very pretty. You just say, I have a web application. It answers to this vhost. And just by saying that, you say, I have an application. It comes from this repository. It comes from this artifact. And this is how you deploy it. It answers to this vhost. You get HA proxy configuration, Nginx configuration, Isinga configuration for internal monitoring, external monitoring via Pingdom or Statuscake or whatever. Isinga mostly stayed out of our way. It did its job with very little complaining, and we complained very little about it. So it was good. It was good. It was really good. The entire platform did the job. It allowed us to pull off a very complex data center / provider failover without losing any requests by building an exact replica of our environment from the old provider at AWS. It let us grow. We added applications to it, mostly without any trouble. and it let us scale out. We added capacity by scaling horizontally or vertically easily as necessary. It was very simple to add more machines of a type and quickly provision them to handle the work. And we didn't need more. It was a small team of about a dozen engineers. We didn't need any more from our hosting platform than it was providing, and we trucked along happily without significant hiccups for about a year. And then I think after about a year of us doing the migration that I talked about 2 years ago, it was the first time I went, we don't really support that. Someone came over and they wanted something. So what was the request? The request was Python 3. And this isn't really something that should be difficult, but it was. Because we had Python machines, and those machines were Python 2, just the question was, do we produce now a Python 3 cluster for just one application? Fortunately, a colleague figured out a way for an application to run either Python 2 or Python 3 on the same box just based on a single configuration setting. So you could quickly try out Python 3, fall back, and so on. But then the next request was Golang, and this was just, I don't know where to even begin. It's, we ship our Python apps to PyPy, which is also a bad decision, but it's the best bad decision, the best bad idea we have. So how do we even ship Golang? I don't even know. So this was roughly the time when I first heard Kubernetes suggested as a solution, or just requested because everyone else is doing it. But I liked what we had. I didn't want to throw it out, certainly not for something like Kubernetes, which would require throwing everything out and replacing it with very similar components that just function slightly differently. We had no in-house expertise or even experience, to be honest, with Kubernetes. And our platform really served us well. It wasn't falling apart. Our platform that we built before the migration and haven't really touched after the migration went from 100 requests per second at peak to 2,000 requests per second at peak. And these days, it never drops below 400. So the minimum that we see now is 4x of the maximum that we saw 2 years ago. And the maximum is 20x. And really, we didn't have to do anything at all. We scaled up the instance sizes for the HA proxies and added a few more workers, but nothing fundamental. So what broke? What really made us pull the trigger? It wasn't the Python 3 or the Golang that really broke it. It was the background workers. It was a perfectly reasonable request from the engineers of an existing Python app. They wanted the ability to process some things in the background, and we had absolutely nothing in our entire toolkit, in our entire platform, to deal with something like that. And we had to go and build it, and it introduced so many exceptions and special cases in our deploy code, in our build code, in our configuration code, that it introduced complexity that eventually introduced breakages and outages that it really shouldn't have. And we spent way too long trying to build the support for background workers for Python. So it became apparent that we reached the end of the road for this platform. We had to figure out what to do next. One of the reasons why this thing broke so easily once we started onboarding new engineers and growing as a company was most of the complexity of each application stretched all the way through the deploy pipeline. If an application had workers, you had to cater for it all the way down to the last step of deploy, which meant we were maintaining a bunch of pipelines in parallel instead of having just one. So what's the answer? It's very clearly containers. There's really no discussion here. So containers concentrate complexity handling in the build stage, where you're building your image, where you're building your container, close to where the complexity originates, so which is the code. Once you have an image, the deploy is exactly the same for everything, regardless of what's inside the container. It doesn't matter if you want to run, Python 2, 3, Go, PHP, Java, Scala, whatever. Once you have an image, that's it. You ship it just like you ship everything else because it's self-contained. Also, things changed in the company, and as the team started growing, we realized that we couldn't support the entire engineering organization through just a small ops team, and we had to hand off some responsibilities and give developers autonomy. So when we started looking into building a new platform, we wanted to make it possible for teams to self-manage most, if not all, of the infrastructure for their applications. So how do I containers? I spent a few days trying to cram containers into our Ansible HA proxy Jenkins setup. And the more I looked at it, the more components I threw out and replaced with more natural fits. So first of all, Jenkins. Jenkins died, and it's been replaced with Travis. Jenkins is self-hosted, so it's either bored or over-provisioned, or another thing you have to manage scaling for. I don't want to be paying too much. I don't want to wait, and I don't want to manage it. So Travis is a much better fit for a high-velocity engineering team because you pay more money and they figure out the scaling. Travis file is also a lot easier to understand than a Jenkins file. It's just Travis file is YAML, Jenkins file is Groovy or some terrible thing. And building container images allows the teams to explain the complexities of their code base locally and to fully control how their applications are built and deployed. So, okay, we have Travis and we've built a container image. What now? How do you run a container on the internet today? There's Kubernetes, a couple other bad attempts at solving the problem, and then a whole lot of nothing, and then ECS. Oh, and also there's Fargate. So ECS, to me, having, by the way, no actual experience with Kubernetes, but ECS to me is Kubernetes built with AWS primitives, having compared the docs and so on. So the services we know and love and have been using for years are what you'll be using to run ECS. So you need a load balancer. You're not going to use some weird software that you've never heard of. You're going to use ELB. You need DNS or service discovery. You're going to use Route 53, and so on and so on. And Fargate, I haven't found a good official explanation for it, but to me, it's serverless ECS. It's ECS, which lets you run containers, just like Kubernetes, but you don't have to manage your cluster to the point where the cluster doesn't exist beyond just like a little thing. You don't say I need 10 workers or 50 workers. You just say run me this container 10 wide or 20 wide or whatever. You get to focus on the code you need to run and its complexities and forget about where it's going to run. Forget about cluster capacity, forget about cluster workers falling over and dying and so on. So just a brief aside about Kubernetes. I am not an expert. I will freely admit that. From what I know, it's a collection of software that makes it easy to start building massively distributed systems and very painful to maintain them in production. I dislike the kitchen sink approach. I dislike the fact that it's just like this all or nothing thing. And if you step out of the use cases that the community is driving, you're on your own. And from what I've heard from people who do actually use it, you need the human resources to run a data center before you consider Kubernetes for production use. I may be 100% wrong. I welcome anyone to convince me otherwise outside this talk. So ECS, Fargate, right? I liked the concept a lot and decided to go for it. I just ran with it. Initial expeditions into it were painful. The console, the web console supporting both classic like vanilla ECS and Fargate is very confusing. So many things to click and enter, and by the time you're done, you've forgotten what you did. You don't know how to reproduce the steps that got you to the success that you've claimed. So Ansible, the thing that we use for config as code, is out, and in comes CloudFormation. CloudFormation is infrastructure as code, and something we had to admit that we didn't have before. I was always telling myself, we're just spinning up machines, and then everything else is Ansible. But the spinning up of machines is what we don't know how to recreate. So CloudFormation is declarative creation of other AWS resources. It lets us deploy the same basic necessities to all our AWS accounts, so we can spin up VPCs, subnets, gateways, firewall rules, ELBs, DNS zones, to all of our AWS accounts. So we have a production account and a staging account and a test account and a dev account, and they all have the exact same resources. And if I decide that suddenly I need another subnet or another ELB, just by adding a few lines to one file, I can have that ELB in all of my accounts within a few minutes. And CloudFormation lets us have individual applications expect to discover those resources within CloudFormation and use them, which means that simple reuse means that app templates are short and only contain the resources necessary for that application. I'll get into the details. So CloudFormation console, I want to call out as the reason why it wins over Terraform, because that's the immediate first question that I hear. As soon as I mention CloudFormation, everyone's like, have you tried Terraform? It has a console inside AWS where you see all of the things that are deployed. That is, to me, in a situation where we have, 50 engineers and this time next year it's going to be 100, that to me means everything. Being able to see which things have been deployed from what template, for what reason, by who, wins over Terraform. I understand Terraform has a cloud console now, but you pay per seat. AWS's is free. Despite the horrible YAML with functions but not variables or loop syntax, which, God, I wish someone would fix inside CloudFormation, but you can see who did what, and you can tear down all resources resulting from a template easily. Just yesterday, we found some resources that were very expensive that didn't need to be there. Just found the template that spun them up, deleted the entire stack, and they disappeared. Icinga, the monitoring thing, is replaced by CloudWatch. Not really much to say here. It's inferior in terms of configurability, frequency, resolution, all of the things. But it wins on the grounds that it just works and doesn't need to be hosted. And once you start using it, you realize it's probably good enough for most of the things that you need monitoring. HA Proxy, the load balancer software that we were using, if we were being honest with ourselves, we weren't using any of its advanced features. And we were already running all requests through ELB to get to HA Proxy to distribute between the redundant HA proxies. So, I'm going to miss its logs. I have pretty logs. But beyond that, there was really nothing that it was doing for us. So what's the actual, this is all, cool, but what's the actual implementation look like? So we have a CloudFormation stack that provides base networking, and like I said, it gets deployed to all of the accounts. It contains the VPC, the subnets for that VPC, the private, the public subnets, and so on, the internet gateways, the NAT, all of that stuff. It contains a DNS zone for that specific account. It contains elastic load balancers, both private and public, should you want to host an application just inside the internal network or publicly. And it contains the ECS cluster and security groups. This is just the definition of a cluster. It's a target for you to deploy your containers into. It doesn't have any machines associated with it. It doesn't cost any money to exist. And we deploy this from GitHub via Travis to all our AWS accounts the second you land a commit. And that stack is depended on by the individual application CloudFormation stack, which has the task definition and service, which are ECS terms for how you defining how you run an application, which container, which image, how many of them you need running, and so on, and including the CPU and RAM spec, how big you need those containers to be. The elastic load balancer target group definition that targets those instances that are running. The listener rule that says, hey, if the user approaches this load balancer asking for www.mydomain.com, send it to this target group. It also contains a log group, so your containers automatically have logging sent to the specific log group for that. It has a task role and policies attached to it. So the task role is what the container runs as, and any attempt to talk to other AWS services is going to be done inside of that, in the context of that role. So if you want your software, your image, to have access to some S3 bucket, you just define the policy right there in the CloudFormation stack. You say, I need this application to have read access to that thing. You can say, I need it to have write access to that S3 bucket. We use the policies in here to allow applications to access their secrets that are hidden in the systems manager parameter store. And also it contains DNS entries. I mentioned in the previous slide we have a DNS zone. So when you run an application with this, it automatically gets its own virtual host. You don't have to go into the main DNS zone and say this application lives there. This you don't have to have app-dev.yourdomain, app-prod, app-test. It's app.dev, and the dev and everything after that comes from the DNS zone before it. So the actual deploy of an application to different accounts can be identical. You don't have to think, is this production? Is this dev? No. In the previous talk we had 12-factor. Yes, 12-factor by all means. The application knows nothing about what it's supposed to be until it boots up and gets configuration. It gets the configuration from the parameter store, and the parameter store tells it, you are staging, this is the database that you connect to, and so on. So everything is in one repository that relates to one application. You have the actual application code, be that Python, Java, Go, whatever. You have the Docker file that explains how the application is built into an image. You have the CloudFormation template that explains which resources the application needs to talk to, how it needs to run, how big of a container it needs, how many containers, and so on. And you have the Travis file that actually explains the interactions between all of these files. You have the Travis file that tells you, when a commit is made on these branches and not on these other branches and by these users or whatever. Here's how you build it. Here's where you ship it to. Here's how you deploy it. So it's easy to follow if you open a repository for an application. You open the Travis file and you see, okay, these are the steps. Build step goes to this, goes to Docker file. Deploy step goes to CloudFormation. Cool. So here's what it actually looks like to deploy a thing. Someone does a push. Let's imagine that it's to a branch that is hot, that is being deployed to something. Travis builds the image and ships it to ECR, that's Elastic Container Repository. Registry, sorry. And then Travis deploy, a second job, will just use CloudFormation to tell Amazon to run that image at that git commit hash or however you want to version your stuff. So Travis doesn't actively touch your stuff, it just supplies the CloudFormation template. And you can have different branches mean different environments. So you can have a dev branch and a test branch and a prod branch. I found a neat micro optimization, which is where if you pronounce the dev branch now production, if it's the same git commit hash, it doesn't rebuild, it just deploys that git commit hash to ECS because the image already exists. It checks if the image exists with that hash. If it does, ship it, because if it's the same hash, nothing has changed in the code, and if there's no configuration in the container, nothing's changed in the container. So what are the benefits of this? What are the immediate benefits that the end users see? The end users here being the developers. All of the context and complexity about an application is in a single repo that is that application. Introducing weird applications and things to the ecosystem, to other apps, doesn't make things weird for others. You don't have weird settings that don't have any effect on you in your templates, in your deploy pipeline. There's no self-managed single point of failure for the applications running. There's ELB, that's redundant. There's ECS, that's redundant. There's no workers that are just yours. There's so yes, if there is a massive region-wide outage, you are in trouble. But there's nothing if it's that, then you're out of luck unless you went multi-region. But if it's not that, then you're fine. There's trivial addition of environments. So if you say, one good example here is long-lived branches for development. So you have tiny changes to an application, but then someone comes along and goes, okay, I'm going to need a long-lived branch for 2 weeks, and we're going to be doing things to it. You can just say, okay, that branch is now something that we deploy. It deploys to a special vhost, and you can have it be continuously deployed separately. Very easy. And a very, very direct example of this is see pull requests live before they merge. So when people open a pull request against an application where we've decided that this is something that we want, they get application-pr26.dev.whatever. And if you're doing visual changes, or if you have a QA department that knows how to test an application, you can test stuff before it merges into before you merge it into your primary development branch. Trivial auto scaling. In the old platform, we had 2 Python boxes, and then the amount of traffic that we were serving just became too much. So we added a third box in a third availability zone, which meant we needed a third load balancer in that availability zone. And once we ran out of room to grow, we had to spin up a whole new cluster, which meant 3 more of these. In CloudFormation with ECS, you can say, okay, this many requests or this CPU load will trigger additional instances of the Docker container to spin up. So you can have your application actually respond to the load and have just your application be responding to the load. ELBs have built-in auto-scaling, and ECS Fargate has built-in load balancing, has built-in auto-scaling. You just have to define your criteria. And I'd just like to briefly touch on the hurdles that we hit in this project. So CloudFormation is extremely fragile starting out. It's a really, really rough experience. It's slightly hostile, really, to start with CloudFormation, and it takes a lot of trial and error to get to a place where you're being somewhat productive. It's worth it. It pays off, and I'm truly enjoying working with CloudFormation right now. But I have to tell you, the first 2 or 3 weeks have been really, really painful. One of my pet peeves is the first deploy of a CloudFormation template failing. You can't deploy over that. If you have something that's working and you say, okay, update it to here, and that fails for whatever reason, it'll come back to here. If you say, here's a new thing, can you deploy it, and it fails, it'll go, nope, this thing is now forever dead, and the only way to fix it is to log in, either use the API directly or log into the console and delete it and then deploy again. So when you're trying out, when you don't have anything, getting to that first stable release is a horrible experience, to the point where I've considered deploying an empty template just to have a stable point. Sorry, that was a long rant. This one I used as an interview question for candidates for the DevOps position for about 2 months, and I didn't hear a good answer. Elastic load balancers previously, historically, did not have virtual host routing. They only had path-based routing. So in path-based routing, it's possible for one rule to catch a wider set of requests than a different rule. So the priority in which they are executed is very important. It's very important. There's also another thing where Elastic Load Balancer will charge you for rule evaluations beyond the 10th rule or something like that. But for the actual proper functioning, of ignoring the building aspect, but for the proper functioning of path-based routing, priority is a thing that is important. So rules have a priority. It's a number. It's a number between 0 or 1 and 10,000. It has to be unique. You cannot have 2 rules that are number 20. And then they introduced virtual host-based routing. Now, virtual hosts either are, like a request either is or isn't, and it's very difficult to have a request that satisfies multiple virtual host rules. But they still need priorities. So if you're adding rules to a load balancer from CloudFormation, if you're using a shared ELB and adding rules to them, each application has to have a unique number. Okay, so this one's going to be 1, this one's going to be 2. But if you want to deploy multiple instances of an application, if you want to have dynamic instances, if you want to deploy pull requests, you truly need persistent, unique numbers that mean nothing outside of the fact that ELB insists that the rules be ordered. I ended up having to write a Lambda that distributes IDs, which is the stupidest possible solution, but it's, again, the best dumb solution that I've heard in over 2 months. But the absolute biggest hurdle in shipping this platform, which was many, many months over the projected delivery date, was building the legacy applications in Docker. I've seen some terrible things that people did over the years that kind of went unnoticed in our build environment. I've seen, applications that build with the destination configuration baked in. So the prod and the dev instances are completely different when they're being built. And this would happen with any tech. So ECS, all of the CloudFormation, all of the things have nothing to do with how painful this project was because of this. And we're still not done. We're still porting applications one by one. Some of them we regularly ship to production. We don't know how they're built. We don't know how to reproduce it with Docker. It's that bad. So if anything, if this is something that you're even remotely considering, start building Docker files, Docker images today. And you will save yourself a world of hurt once you actually pull the trigger on something like this. Questions? I'll repeat.
Congratulations. This whole process of trying to find the right solution, how long did it take you to reach this state today?
The question is, how long did it take to get to here? I shouldn't answer. There was the project wasn't top priority. Months. I've been thinking about it for like a year. So like last summer of 2018 was when we had that Kubernetes question mark moment. And I was like, no Kubernetes, please, no Kubernetes, we'll figure something out. And then I said, we'll do like the next migration, I know we can do it. And then that was the background workers thing, and that took forever. We almost died. It was in December. And then I would say that I started actually looking into CloudFormation and ECS around March of this year. But it was just me. I have other high priority projects. Things keep breaking and we have to put out fires. So it's not, I would say 6 months, but it's not 6 months of full-time effort. And it was just me for the most part. I now have people helping out with the fringe parts of it. But yeah, 6 months is 6 months to, well, that's not actually fair, because once we have something working, then we eased off the throttle and now we're slowly migrating the applications. But to get to something running, 3 to 4 months, running in production. So we have things in production with this, but we still have a long way to go to port all of the old stuff. Thank you for the question. Any other? Yes?
Do you have any mechanism of testing the CloudFormation stack before you roll it onto production?
So the question is there any method of testing the CloudFormation stack before rolling out to production? Yes, don't roll out to production for every single commit. Roll it out to your dev, test, staging cluster, and so on. So the idea behind 12-factor stuff that was mentioned in the last talk is you ship the same code to any environment and the configuration is different. That minimizes the chances that something falls apart between staging and production, or dev and production. It doesn't kill it completely, because there's always going to be, if environment equals prod, then do this. But it does improve things significantly. So I would say anyone today serving any sort of meaningful traffic, shipping every commit out to production, there's no way to do that safely. You're going to have something fall over. The only thing you can do is have canaries. So you ship to dev, then you ship to test, to staging. If all of those work, then you ship to production, and you have rollbacks and so on. You have automatic rollbacks if things don't work. I don't think there's any way to ship every commit to production and have it be safe.
Just one regarding the CloudFormation, really. We just had discussion the other day. Did it ever happen that CloudFormation deleted stuff or touched stuff which were not supposed to be touched? Like when you delete a stack, did it ever happen that it did something wrong?
So the question is, did we ever experience CloudFormation deleting things that it shouldn't delete when you delete a stack? So you mean you delete a stack and something disappears that wasn't provisioned from that stack? Yeah. I have not experienced that. I've not heard of that. I'm sorry.
Oh, I'm not sorry. It's good.
Yeah.
Just to add things to CloudFormation testing, besides pushing it to dev and staging, there's also 3 tools that you can use: CFN-Lint, CFN-Nag, and TaskCat. Those tools help you test and evaluate your CloudFormation templates in a pipeline.
Okay, cool. So there are tools to test CloudFormation templates, yes. I knew about the lint. That is not where I was having problems. So I didn't find that stuff useful. But yes, there are certainly tools. And CloudFormation, when it first started, was terrible. It is now significantly less terrible. And I'm seeing more and more adoption around it, so more and more tools around it are surely to follow. Last question.
Are you running on Fargate only, or you're using regular ECS as well?
The question is, are we using only Fargate or also regular ECS? We're using only Fargate because I I haven't, because why would you run regular ECS? Strictly for cost reasons, right? Fargate is slightly more expensive. No? Performance. Okay, we haven't, for the stuff that we do. So this is web applications that, you know, go over the public internet. We have not noticed any performance issues. So my pitch for Fargate is, it's at the very least nice to roll things out onto it. And if you have a high performance, you know, if you have a use case where Fargate starts to not deliver, then you're more than welcome to spin up. Like CloudFormation ECS regular is slightly more complex because of you having to juggle the actual workers and so on. But it's the path to migration is very, very clear. So if it ends up costing too much money, or if you have performance issues, you're not stuck with the technology that you know. But no, I haven't touched regular ECS. Okay, I think that's time for lunch. Thank you.